Okay. Hello. I would like first to thank the organization team of the Summer School and Symposium for the incredible job during this year. I would like also thank to my colleagues at the Color Imaging Lab, Professor Juan Nieves, Miguel Ángel Martínez, and Luis Gómez Robledo, who collaborated in this study, developed in the optics department at the University of Granada, Spain. So I'm going to be talking to you about what simulated observers with color vision deficiencies consider as relevant colors in paintings and show the difference in the number of relevant colors compared to subjects with normal color vision. I will start off by giving you an overview of the problem. Color plays an important role in the creation of art. Numerous studies have shown a direct link between color perception and emotion. While there is still some debate over exactly how many colors can a normal trichromat perceive, the estimations suggest it is within the range of millions number of discernible colors. Despite this, an observer cannot differentiate or retain this quantity of discernible colors when viewing a natural or artificial scene. This an initial number of millions signal from photoreceptors at the retina level is reduced when the information leaves the retina. So in this bottle-like context, the concept of relevant colors describes the number of colors that would catch our attention when we look at a painting. This provides valuable insights for the development of tools such as color palettes, extractors. There are many examples about the interest in extracting the color palette of images. For example, in the tool offered by the Adobe Color platform, you can find the color palette from any image you upload, or this one from Canva. However, these approaches usually work with a fixed number of colors. In this example, 4 or 5, as a result of applying clustering approaches. However, due to various circumstances with a genetic or acquired origin, the functioning of the cones in the observer's retina can change color perception, and this phenomenon enters in which we call it as color vision deficiencies. This condition affects a significant portion of the population, with a notable prevalence in males, around 8% in the European population, while it is less common in females, about 0.5%. People with color vision deficiencies can be grouped into 4 categories anomalous: trichromats, dichromats, monochromats, and achromats. Anomalous trichromats have an anomaly in one type of cone and are further divided into anomalous, deuteranomalous, and trianomalous, depending on the affected cone. The chromats, on the other hand, have only 2 types of cones and are divided into protanopes, deuteranopes, and tritanopes. Blue cones monochromats lack 2 types of cones, having only the blue cones. And finally, achromats lack any photopigments. In this slide, I show some of the everyday challenges faced by individuals with color vision deficiencies, identifying the ripeness, fruit, combining clothes, recognizing traffic light colors, reading maps, or watching a football match. So, considering all of this, what do observers with color vision deficiencies consider as relevant colors in paintings? Well, in a previous computational analysis, we opted to address this issue based on 2 main working hypotheses. First, color categorization that has proven effective for many tasks, such as search, identification, recognition, and classification. We can simplify the description of a large set of colors to a small number of color terms, which are representative of all possible color clusters in color space. Second assumption, the chromatic diversity notion. As pointed out by Professor Nascimento and his colleagues, the chromatic diversity of paintings is aligned with the natural environment, being the number of discernible colors an appropriate way of describing the number of colors of a painting and its color gamut. In addition, we use large color difference to segment the color gamut of a painting. And instead of using just one side of color difference to compute colors, we try cube grids n times larger than the discernible color grids. In the current study, we have used a single image dataset containing 15 images from the Prado Museum. As you can see, the images contain a spectrochromatic information. We use data from the study by Nieves and his colleagues from the psychophysical experiment with normal vision observers to find the relevant colors that describe the color palette of a painting. This is important because we can compare the relevant colors identified by subjects with normal color vision to relevant colors identified by simulated subjects with color vision deficiencies. The next step is to daltonize the images to simulate how people with a severe degree of color vision deficiency will see them. For this, we use the algorithm created by Machado and colleagues, a physiological-based model for simulating color perception, based on the stage theory of human color vision. This algorithm takes into account the cone spectral sensitivity functions for an average normal trichromat. Machado's algorithm modeled anomalous trichromacy by shifting the spectral sensitivity function of an anomalous cone according to the degree of severity of the anomaly. In our experiment, we shifted 20 nanometers representing a severe case of every anomaly. And finally, the simulation for a normal trichromat on the color perception of an anomalous trichromat is obtained with this equation. And here are 3 examples of daltonized images using the previously mentioned algorithm. The first image is a Delphin simulation, the second is a Proton simulation, and the third is a Triton simulation. With the algorithm introduced by Nieves and colleagues, we calculate the relevant colors for our set of daltonized images. To get the relevant colors, the first assumption is to use large color difference to segment the color gamut of the corresponding painting. And instead of using just one side of color difference to compute colors, as it is the case when you count the number of discernible colors in an image, the algorithm tries cube grids n times larger than those discernible grids. And the second assumption is some restrictions to the L and chroma values for each pixel. Restriction for L affects not only the computation of dark pixels, but adding also restrictions for bright and saturated pixels. To address problems of under-segmentation, which means getting images with unreliable color palettes or obtaining images with very few colors, this algorithm minimizes errors by tuning parameters, such as testing different values for the cube grids and selecting optimal threshold in L and chroma values. Let's have a look at the results. This plot is an example of the relevant colors found in the simulated painting in Journal de Math, painted by Pradilla in 1877. The plot of the right shows the A and B colors component of relevant colors, these blue crosses, superimposed over the color gamut, red points, spanned by all the colors in the image. The number of relevant colors simulating the 3 severe color vision deficiencies was 14 on average, which is a very small number of colors in comparison with the potential number of thousands of discernible colors that we could obtain in those images. The histogram shows the results of all paintings simulating the 3 vision deficiencies. Taking account the psychophysical results, the number of relevant colors with normal color vision subjects is 19. The minimum number for the Prado set corresponded to this painting, Charles V, with only 9 colors. And the crucifixion painting by Juan de Flandes from 1519, who got around 22 relevant colors, a relatively large number of subjective colors in accordance to the spectrochromatic content of the image. And this brings me to the conclusions. First, we have introduced a method to obtain the subject relevant colors that describe the color palette for painting for simulated CBD subjects. Second, we got an average number of 14 colors with all the simulated CBD paintings. This number was lower than the average number of colors found for normal color vision observers, as we expected. In this case, 19. This reveals that dichromatic observers affects how mental impression of the observed painting is degraded. And third, there were no significant difference between the different types of color vision deficiencies. I mean, between deutan, proton, and triton subjects, with numbers of relevant colors around 13 and 14. And finally, we were able to use those relevant colors as instances or to enable segment colors images. Of course, this does not mean that color deficient observers will perceive images as a copy of those relevant colors instances, but is an indicative of the color information they are able to retain. Thank you for your attention.
So thank you. We have about 3 minutes for questions. So please raise your hand for questioning, then we will unmute you for asking the question. So before anybody else raises their hand, maybe perhaps I could ask, so in what sense you are simulated relevant color? Do they compare well with the actual relevant colors identified by these color deficient observers?
Well, we use two different algorithms, one for the simulating CBD subjects and other one for calculate or compute with the algorithm created by Nieves and his colleagues.
Created by, but it's also an algorithm, or it is actually by observers pointing out relevant colors. Are they both algorithms? Is there any data that is by observers actually pointing out what are the relevant colors to them?
For the data creating the observers, we use the physical experiment with Nieves, and for taking all the relevant colors, we use first the algorithm created by Machado to simulate the CBD or the color vision subjects with these images.
I understand you use the simulated color. What I mean is, do you have data actually from these observers to point out to you what are the colors relevant to them? Whether your simulated color corresponding to the relevant colors of the observers, do you have such data?
Yes, you can find in this reference is 5, 6, and 7.
I see. So you actually have these data. So what is the rationale for using simulated relevant color rather than real relevant colors by these subjects?
Of course, in this moment, we don't have the data from the CBD subjects, only with the color vision normal subjects. So we need first to simulate with another algorithm, in this case, the Machado algorithm.
I see. Well, thank you.